In summarizing what we've looked at with graphs, we're going to finally talk about asymptotes and holes. You may have seen asymptotes before. If I have a graph, and it looks something like this, you may have seen graphs like this before. We have what's called an asymptote. This right here, this green line, that is a vertical asymptote. And notice how this red line, the red curve, as it goes to positive infinity for y, it's going to get closer and closer and closer to that asymptote, but never actually touch it. Same with down here. This is going to curve downward and get closer and closer and closer to that asymptote, but never touch it. This blue line, crudely drawn, is the horizontal asymptote. And the same deal, it's the same asymptotic is the adjective, asymptotic behavior, asymptote. And we can see that as x goes to positive infinity, this y value is going to get closer and closer to this asymptote, but never actually touch it. So this is asymptotic behavior. We can find these in graphs just by looking at them. However, how do we find these algebraically? Well, vertical asymptotes are going to exist where the graph does not exist. So finding vertical asymptotes are going to be where the function is undefined. Now, if we look here, this is a fraction. Think to your knowledge about fractions. Where is the fraction going to be undefined? This fraction is going to be undefined whenever the denominator is 0. So I more or less ignore the numerator, and I take this denominator and I set it equal to 0. I see where this is going to be equal to 0. So x squared minus 1, I add 1 to both sides, so x squared is equal to 1. I take the square root, so I get x is equal to plus or minus 1. These are two vertical asymptotes. So the vertical asymptotes are going to be at x is equal to 1 and x is equal to negative 1. Now notice how I wrote these answers, x equals, x equals. Those are equations for vertical lines. And we can see that the vertical asymptote is a vertical line. So that means that I write my answer as x equals. And that's all I have to do. Just take the denominator, set it equal to 0, and solve. Now, horizontal asymptotes, there are 3 rules. We want to look at the degrees. In the numerator and in the denominator. So we're going to have f of x equals a to the x to the n and bx to the d, where n is the degree in the numerator and d is the degree in the denominator. Now there are 3 possibilities here. Either the degree in the numerator is larger than the denominator, or it's less than the denominator, or they're equal. Now, whenever the degree in the numerator is larger than the degree in the denominator, it's really simple. There is no horizontal asymptote, and that's perfect. If the degree in the denominator is larger than the degree in the numerator, then it's a horizontal line. All of these are horizontal asymptotes or horizontal lines. So it's going to be y equals, it's going to be y is equal to 0, always. No matter what the degree is, no matter what the values of d and n are, if the degree in the denominator is larger than the degree in the numerator, there's a horizontal asymptote and y is equal to 0. And it's equal to 0. That's not what I meant. If n is equal to d, so if the two are equal to each other, such as in this example, then what I do is I take the leading coefficients and divide them. So here the leading coefficient in the numerator is a, the leading coefficient in the denominator is b. So what I do is a divided by b, and it gives me this fraction. So here in this example, I can see that n is equal to 2, the degree in the numerator. The degree in the denominator is also equal to 2. So because they are equal, I go to this third option, and I find that my horizontal asymptote is equal to y is equal to the leading coefficients. So 2 divided by 1, so y is equal to 2. For vertical asymptotes, you actually have to do some work, but for horizontal asymptotes, there shouldn't be any work, but you do need to remember these conditions. And finally, what about a whole? Well, if you notice, I have this fraction that is made up of two polynomials that we can factor. So let's factor them first. So x minus 2, actually it's an x plus 2, x minus 1. In my denominator, I'm going to have an x plus 2 and an x minus 3. Now, if you remember, we said that vertical asymptotes are values that make the denominator 0. However, if I were to graph this, I would only find a vertical asymptote at x is equal to 3. Even though if I plug in x is equal to negative 2, that would make this denominator 0. And the reason is because I can cancel out these two factors. So whenever we have two factors in the numerator and the denominator that are the same, what we can do is we can obviously cancel them out. We call this removable discontinuity. And this removable discontinuity will give us our wholes. So I take whatever factors I can reduce in my numerator and denominator and set them equal to 0. So x plus 2 is equal to 0. So that means that we have a whole at x is equal to negative 2. But we have to bear in mind that this is actually technically a point, even though we are writing it as x equals. So just understand that for a whole, it's a point. And if I go back to that graph I drew way back in the beginning, a whole could be anywhere here. A point doesn't have any dimensions. We can't see a point. So if I were to actually graph this, I would draw an open circle. And that would be a whole, where the graph does not exist. It's a little bit better, right? Where the graph does not exist. But if I were to graph it on a graphing utility like a calculator or software, it wouldn't look any different to us because we can't see the whole. But if we were to graph it by hand, we would draw an open circle to show others. So make the denominator 0. Any factors that can't be removed will give you a vertical asymptote. Any factors that can be removed with the denominator, or sorry, with the numerator, will give you a whole. So let's put it all together. So actually I have this same function as before. So I know that my numerator factors to x plus 2 times x minus 1. And in the denominator, it's going to be x minus 3 and x plus 2. Actually, let me change the order of that. So I can actually write the x plus 2's on top of each other. Okay, so let's start with a vertical asymptote, because that's what we just went over. Vertical asymptote here, we know that if I look at these factors that are the same, it's going to be the x plus 2's. The value of x that will make the denominator 0, no matter what I factor out, is going to be x is equal to 3. That means that the whole is going to be x is equal to negative 2, because that is a factor in both numerator and denominator. The horizontal asymptote, I look at the degrees. Because the degree in the numerator and denominator are equal, I divide the leading coefficients. So this is y is equal to 1 divided by 1, which is 1. Now, for the x-intercepts are where y is equal to 0. So if we think about this, it's going to cross the x-axis at y is equal to 0. What's going to make a fraction equal to 0? Well, if the denominator is equal to 0, it's undefined. But if the numerator is equal to 0, that will give us y is equal to 0. So we set the factors that we did not pull out, so this x plus 2 does not count. If we set this numerator of x minus 1 is equal to 0, we get that our x-intercept is at x is 1, so the point would be 1, 0. Now the y-intercept, remember, this is where x is equal to 0. So y is going to equal 0 plus 0 minus 2 over 0 minus 0 minus 6. So I get negative 2 over negative 6, which is 1/3. So x is 0, y is 1/3, and that's the point for my y-intercept. I will give you charts like this, and all you have to do is fill them in. Remember, x-intercepts, for fractions, you make the numerator 0. For y-intercepts, you turn x into 0. Vertical asymptotes, which values will make a factored denominator equal to 0. Horizontal asymptotes, look at those degree rules. And for wholes, which values would make the denominator 0, but have the same factor in the numerator. So get some more practice on this. We will practice in class, and let me know if you have questions.